Welcome to Chapter 9. This chapter is going to deal with sequences, series, and probability. This is going to be the first part of Section 1 that deals with sequences and series. When we're talking about something being sequenced, we mean that it has an order, where we have a first member, a second member, a third member, or a first term, a second term, and so on. We want to think of a sequence as a function that has a domain that has positive real numbers, and we're going to think of it like as a function where f of 1 would equal a sub 1, f of 2 would equal a sub 2, or your first term, your second term, your 10th term, or whatever, and so on. So instead of using function notation, we're going to use what we call subscript notation. And remember that the little number that falls below is the subscript. Now, an infinite sequence is a function whose domain is a set of positive integers. And the function values a sub 1, a sub 2, a sub 3, whatever term we're looking at, these are called terms of the sequence. And if the domain of your function consists of the first 5 terms or the first 6 terms, then we say it's finite. If the function or the sequence continues to go on, then we say it's an infinite sequence. So, for our first example, we're going to write the first 5 terms of the sequence. And we are given that a sub n equals 2n plus 1. So if I want to find my first term, or my a sub 1 term, I'm going to plug in this number right here, or the subscript, means that's what I'm going to be plugging in for this n. So I have 2 times 1 plus 1 is equal to 3. My a sub 2 term is going to be 2 times 2 plus 1, which is equal to 5. My a sub 3 term is going to equal 2 times 3 plus 1, which is equal to 7. A sub 4 is equal to 2 times 4 plus 1, which is 9. And my a sub 5 term is equal to 2 times 5 plus 1, which equals 11. For part B, we're going to do the same thing. A sub 1 equals 2 minus a negative 1 raised to the first, which is really 2 minus a negative 1, or 3. A sub 2 equals 2 minus a negative 1 raised to the second. A negative 1 squared is really a positive 1, so I end up with 2 minus 1, or 1. A sub 3 is equal to 2 minus a negative 1 to the third, which is going to keep that a negative, so 2 minus a negative 1 is really going to give us 3. A sub 4 is equal to 2 minus a negative 1 to the fourth, which is going to give us 1. And a sub 5 is equal to 2 minus a negative 1 to the fifth, which is going to keep that 1 negative, which is going to give us 3. Example 2 says to write an expression for the apparent nth term of each sequence. So in other words, what we're going to do is we are going to come up with the equation or formula that each of these terms are coming from. So what I will do is I always start out by identifying what n equals. So my first term equals 1. My second term equals 5. Third term is 9. Fourth term is 13. My fifth term is 17, and so on. From here, it just becomes kind of a game of trying to find what pattern goes. My best suggestion to you is I like to kind of start out with these middle terms and see what's going on. I see that if I go from 1 to 5, I have a difference of 4. 5 to 9 is a difference of 4. 9 to 13 is a difference of 4. So they all have a common term of 4. However, I also have to keep in mind that I'm dealing with these terms here. So I know that if I have to do something with 2, whether it be add, subtract, multiply, divide, raise it to a power, and I'm going to end up with a 5. So if I look, I see that if I take 2 and I square it, let's say I'm going to get 4. But if I go to my third term, I can go 3 squared gives me 9, so that works. If I go 4 squared, that gives me 16. So when I get to my fourth term, that doesn't work. What I do notice though is that if I go 4 times n, I can subtract 3, and that will give me my a sub n term. So let's just double check our work. 4 times 3 minus 3, does that give me 9? Yes. 4 times 4 minus 3, does that give me 13? Yes. 4 times 5 minus 3, does that give me 17? Yes. So I know this equation right here then will work. I'm going to start out doing the same thing for part B. So my first term is going to equal 2, my second term equals negative 9, my third term equals 28, fourth is a negative 65, and my fifth term equals a negative 65. Or I'm sorry, a 126. Then I'm just going to kind of start playing around with things. Can I go 2 squared to get 9? No. I know that 2 squared minus, something, you kind of have to start playing around with those types of rules. Now, right now, I do notice that my signs alternate. Okay, I'll show you how to take care of alternating signs here in just 1 second. So let's just deal with the 2, the 9, the 28, the 65, and so on. As you do more of these, you will get better with them. But I notice if I cube, so I'm looking at my a sub n term, if I cube each term, 3 to the third power is going to give me 27. I can add 1 to that. So if I go n cubed plus 1. Now let's do the same thing. 2 cubed is 8, plus 1 is 9. Same thing if I go 4. 4 cubed is 64, plus 1 is 65. And it will work for all of the terms that are given. Now, I have my number piece. Now I need to go in and account for the negative sign. I notice that my sign is positive on the odd number terms, or that my negative sign occurs on even number terms. So what I'm going to do is I'm going to multiply this by a negative 1, and I know that I need to raise this negative 1 to something that will give me a negative number, because negative 1 to raise to an odd number. Negative 1 raised to any odd power will keep that negative 1 in negative. If I raise the negative 1 to an even power, it will make it a positive number. So in this case, if I go negative 1 and I raise it just to the power of n, and let's use the example of 2 here for n, negative 1 squared, that's going to give me a positive number. So I can't have n, but I can go in and make this n minus 1. So now if I plug in a 2 for that n value, I'm going to say negative 1 raised to the power of 2 minus 1, which is 1. Negative 1 to the first power is still a negative 1. Let's double check it for the fourth term. If I go and I plug a 4 in for n, 4 minus 3 is going to give me, 4 minus 1 is going to give me 3. Negative 1 to the third power is still going to give me a negative 1. So this works. And just a side note that I did put down here is you need to list more than the first few terms to define a unique sequence. Okay? Like I told you before, I kind of have to start in the middle, okay, for me. And sometimes you'll find that you'll get a pattern that works for your first 2, maybe the first 3 terms, but it doesn't work after that. So make sure you double check that all of your given terms will work in the function that you have created. We'll find that some sequences are also going to be defined recursively, and they need to be given more than the first few terms, because we're going to have to use previous terms to find the next term. An excellent example of this is called the Fibonacci sequence. Okay, and in this case, we're given a sub 0 equals 1, a sub 1 is 1, a sub k equals a sub k minus 2 plus a sub k minus 1. Now don't get caught up on all of your subscripts. This k value is kind of what we were referring to as n before. K minus 2 says if I want like the third term, I'm going to subtract 2 from it, so I'm really going to plug in my a sub 1 term if I'm looking at my third overall term. And I'll show you what we mean here. So let's look at our a sub 0 was given. We know that that's 1. A sub 1 was given. We know that that is also 1. Now we have to go in and find a sub 2. Well, a sub 2 means I'm going to take a and go 2 minus 2 plus a sub 2 minus 1. Now I know that a sub 2 minus 2 is really going to give me a sub 0 plus a sub 2 minus 1 is really a sub 1. Now from up above, I know that a sub 0 is equal to 1 plus my a sub 1 term was also to equal to 1. So this gives me 2 for my a sub 2 term. Now I'm going to do the same thing for my a sub 3 term. A sub 3 becomes a sub 3 minus 1, 3 minus 2 plus a sub 3 minus 1. Well, my a sub 3 minus 2 is really my a sub 1 term plus my a sub 2 term. A sub 1 we said was equal to 1 plus my a sub 2 we just found was 2, and this is going to give me 3. Now my a sub 4 term is going to be a sub 4 minus 1, which is a sub 3. It's 4 minus 2, which is going to give me 2, plus my a sub 4 minus 1, which is 3. My a sub 2 term we said was 2, plus my a sub 3 term, which was 3, and 2 plus 3 equals 5. And I'm going to continue to do these for my next couple of terms. So a sub 5 is equal to my a sub 5 minus 2, which is 3, plus a sub 5 minus 1, which is 4. A sub 3 we said was 3 plus 5 equals 8. And my last term is going to be a sub 6. So a sub 6 minus 2 is going to give me a sub 4, plus a sub 4 minus 1, which is a sub 5. We said a sub 4 was equal to 5, plus 8 is going to give me 13. So my first 6 terms are going to be the 1 here, 1 here, 2, 3, 5, 8, and 13. The next thing we're going to look at is factorial notation. If n is a positive integer, then n factorial is defined as n with an exclamation point. The exclamation point means factorial. And I think you've had this before, but in case you haven't, the factorial means that we're going to go 1 times 2 times 3 times 4, all the way up to the n minus 1 term means that if n is 5, n minus 1 is going to be 4. So I'm just going to continue to multiply consecutive terms by each other until I reach that given number. So the one thing we have to look at is a special case. 0 factorial does equal 1. Just like 1 factorial equals 1, 2 factorial is 1 times 2, which is 2. 3 factorial means 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 24, and so on. I believe the factorial button on your calculator is underneath the math, and you may have to scroll over to one of the menus at the top, but it is on your calculator somewhere, and we can go over that function when I return to class. The last thing I want you to know about factorials is that these follow the same order of operations as your exponents do. So if you have something with a factorial, treat that like an exponent. So let's go ahead and look at our next example that says write the first 5 terms of a sub n equals 3 to the n plus 1 divided by n factorial. And it tells us that we're going to start out with n equals 0. So that tells me that a sub 0 is going to equal to 3 to the 0 plus 1 divided by 0 factorial. Well, I know that 3 to the power of 0 is 1 plus 1 divided by 1 factorial, which is also 1. This is going to give me 2 divided by 1, which is equal to 2. My a sub 1 term is going to be 3 to the first plus 1 divided by, 1 factorial, which is 1. And this is going to give me 3 plus 1 divided by 1, or 4. A sub 2 is going to be 3 squared plus 1 divided by 2 factorial. 3 squared is 9 plus 1 divided by 2 factorial, which is 2. I end up with 10 halves, or 5. My a sub 3 term is going to be 3 cubed plus 1 divided by 3 factorial. 3 cubed is 27 plus 1 divided by 3 factorial, which is 6. So I end up with 28 sixths, which reduces down to 14 thirds. And right now I have 4 terms, so I need to go up to 5. So I will do my a sub 4 term. This is going to equal 3 to the 4th plus 1 divided by 4 factorial. That's going to give us 3 to the 4th is 81 plus 1 is 82 divided by 4 factorial, which is 24. And 82 24ths will reduce down to 41 twelfths. Our next example deals with fractions and factorials because we can actually reduce factorials within fractions. If we go ahead and write out what it means to be 9 factorial, I have 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, delete that out, times 9, and I'm going to divide that by 1 times 2 for my 2 factorial, and 1 times 2 times 3 times 4 times 5 times 6 for 6 factorial. Now what I see is I have common numerators and common denominators that will actually cancel out. So I have 1, 2 are going to cancel out here. Then I have 3 and 3, 4, 4, 5, 5, 6, and 6. So what you're really left with then from the numerator is I have 8 times 9 divided by 1 times 2. 8 times 9 gives me 72. 1 times 2 is 2. 72 halves is really equal to 36. And 36 then would be my final answer. I can do the same thing with part B. I'm going to go 1 times 2 times 3 times 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. And I'm going to divide that by 1 times 2 times 3 times 4 times 1 times 2 times 3 times 4. My 1's are going to cancel, 2's, 3's. Then I have 1, 2, 3, and I'm going to go back and cross out this 4 here. So what I end up with then is 5 times 6 times 7 times 8 divided by 4. And when I simplify that, 5 times 6 times 7 times 8 is really 1,680 divided by 4, and you'll see that this is 420. Now for this last one, where I'm using arbitrary terms like n plus 1, n plus 1 factorial really means I'm going to go with the first term times my second term times my third term times, and I'm going to put all of these terms in between n, and then I'm going to multiply that by one more term, which is my n plus 1. Then I'm going to divide that by n factorial, which is 1 times 2 times 3 times all the terms between 3 and n. Now if you don't understand where I'm getting this, please make sure to ask me because you will see problems like this again. So we have to understand this. So then what's going to happen, my 1's are going to cancel, my 2's are going to cancel, 3's are going to cancel, all these terms in between 3 and n, my n's are going to cancel, and I'm going to be left with n plus 1. And that's my final answer for part C. Your fun fact for this video deals with seniors. It is the Wednesday before the end of your third marking period. That means you have 1 marking period and 3 days left. Juniors, you have 1 year 1 marking period and 3 days left until you graduate. Sophomores, sorry to say you still have 2 years, 1 marking period, and 3 days. On that note, have a good night.